Welcome to CAT Tutorials, and in this video I'll be covering practice problem 3.2 from the 4th edition of Fundamentals of Electric Circuits. Now if you have a different version, you can basically just apply what I'm going to show you to the values which you might have in your textbook. Okay, so let's go ahead. The question asks us to find the node voltages, and the voltages of interest, or the nodes of interest, are 1, 2, and 3. So now we're going to use nodal analysis and Kramer's rule to solve this problem. So let's start. We're going to start at node 1, or at V1. Let's call it V1. So at V1, which is basically here, let's check all the junctions or all the currents of interest which we have here. So I'm going to have a convention for all of these to say if a current is going into a node, then I'll assign a negative sign to it. And if a current is going out of the node, I will say it is positive. So let's start finding our currents, or just making an equation for our problem, right? So at the node V1, which is over there, we have 10 amperes going in. So as I said, in is negative in my case. So I'd say negative 10. And here I'm going to take it from this node to that node, saying V1 subtract V2, as potential difference is the voltage, or is between 2 points. And that's basically why this is what you do in nodal analysis. You're interested in finding, so using the Ohm's law, which says V is equals to IR. So this V is between 2 points mainly, and I, which is the current which you're basically interested in, is equals to V over R. Now that this V is between 2 points, then we have to find the potential difference, or the difference between the 2 points, and divide by the resistor value. And in this case, the resistor value is 3. So V1 minus V2 to show that the current is going out. That's why I have a positive sign there. So from V1 to V2, we have a current which passes through 3, right? And I'm going to do the same thing up here for the current which passes through the 2 ohms. So between node 1 and node 3, we have 2 ohms, and that should amount to 0, right? So that's for the first node. That's for the first node, node 1. So let's go to node 2, or V2. So the first thing you're going to notice here is Ix has been labeled as going downwards. And I said, if it's going out of the node, I'm going to say it's actually positive. So this Ix here, so we're going to say Ix, we have a relationship between the node itself and the resistor and the node voltage. So Ix, if you can check, I basically said potential differences between 2 points. And this point has been highlighted as the ground, or the 0 volt node. So this V2 minus 0, which is between these 2 points, is basically the same as just V2, right? And then the current goes down into a resistor of value 4. And that's the relationship which you basically have between Ix and the node voltage. So now we're currently at this point here, right? So let's add up all the currents and form an equation. So we're going to say V2 minus V1 to show that the current is going out of here. So we're going to have it as positive. So V2 minus V1, right? V2 minus V1, and it passes through a resistor of value 3. So we're going to have V2 minus V1 over 3. And we're going to say Ix plus Ix, which it's going out. So I'm going to say it's positive, plus Ix, right? And finally, we have 4Ix, which is going into the node. So it's going to be negative 4Ix is equals to 0. But now we said Ix is equals to V2 over 4. So we just substitute that into there. So V2 minus V1 divided by 3 plus V2 divided by 4, minus 4 multiplied by V2 divided by 4. And that is your equation for the second node. We now move on to the final node, which is, let's call it V3 as well, just following what we've been doing. So V3, let's write it down here. So we have, if you can look, you're basically just going to do the same thing. Between 3 and 1, we have 2. So V3 subtract V1 divided by 2, which is the resistance between the two nodes. And then we have this going out, 4Ix is going out in this case for the third node. So it's going to be positive, and I'm going to say plus 4Ix. And finally, you're going to say the current through here is going downwards. So you're going to say V3 minus 0 divided by 6, which is basically V3 divided by 6, right? And all of this equals to 0. Now let's simplify all of these equations and see where we can go from there. So the first equation, what you can do to simplify this is to say, you're gonna multiply all of it for V1, you're gonna multiply all of it by 6, right? And you're gonna have negative 60 plus 2V1, negative 2V2 plus 3V1, negative 3V3 is equals to 0. And finally, you're just going to add the like terms. So you have that. So that's going to be 5V1. And you have that. And that is alone. Right? And that is also by itself. And we're going to take the 60 to the other side. Right? So that's basically what we have for the first equation. This is the first equation from node 1. That's basically what we got. Now simplifying the second equation from node 2, which is here. So we're going to multiply by 12, right? Multiplying by 12, we're going to have 4V2 minus 4V1 plus 3V2 minus 12V2, amounting to 0. Adding the like terms, we have negative 4V1. And add those, we have plus 7V2. Right, plus 7V2. Let's see. No. We also have that. So plus 7, it's going to be negative 5. Right? It's going to be negative 5 because it's 4 plus 3, which is 7, minus 12, which is negative 5. And finally, we're going to have plus, no, we don't have the third term. So that's basically all we have for the second equation. This is the second equation. And then, am I missing something? Let's see. No, I'm not missing anything. So now we move on to the third equation. Let's simplify the third equation. So we're going to multiply everything by 6 in this case. So we're going to have 3V3, right, minus 3V1. And we said Ix is V2 over 4. So we're going to say plus, since multiplying by 6, I'm going to say 6 multiplied by 4 multiplied by V2 over 4. So that cancels out. You're only left with 6V2. And finally, we have plus V3 is equals to 0, right? And your final equation is going to be negative 3V1, right? Plus adding, only have that. So it's going to be plus 6V2. And finally, we're going to have V3 added to that is going to be plus 4V3 is equals to 0. So these are the three equations which we have. Now, trying to solve these using basic simultaneous methods could be tedious. So I'm basically going to use Kramer's rule to find each of the variables of interest. So let me just write all these equations up here again so that I can have some space to do Kramer's rule. So let's write all the equations quickly. So 5V1 minus 2V2 negative 3V3 is equals to 60. That's the first equation. Second equation is negative 4V1 minus 5V2 is equals to 0. And the last equation says negative 3V1 plus 6V2 plus 4V3 is equals to 0, right? So those are the three equations which we have, and the three equations which we have to solve to find each of the node voltages. So let me just erase everything else, and then so I can do Kramer's rule. Now, if you are unfamiliar with Kramer's rule, I have a video up which explains how to do that. So basically, Kramer's rule, you just use it to solve a bunch of equations or a system of equations in a simplified manner. So we're going to transform this system of equations into matrices, or as, a matrix, basically. And the general form of that, just a quick recap, is AX is equals to B. So the A matrix consists of the coefficients of each of the variables, right? So let's do that. So we're just going to plug in all of these coefficients, 5, -2, like that, to form a matrix. And that we're going to call the A matrix. We have 5, -2, -3, -4, -5, 0, because there's no V3 term in the second equation. And then finally, you're going to have -3, 6, and 4. So -3, 6, 4. And the variables of interest are V1, V2, and V3. And equals to the B matrix are the constants on the other side of the equal sign. So we transform this system of equations into this. So wrote it in matrix form. And so, as Kramer's rule says, xk is equals to delta k divided by delta. So let's find this basic delta, which is the delta of the A matrix, which is the determinant of this matrix as it is, right? So let's do that quickly. So delta is equals to the determinant of 5 minus 4 minus 3 minus 2 minus 5, 6, -3, 0, 4, right? Determinant of that, closing the in there, we have 5. So this is 5 multiplied by -5, 4, and you have -0, right? And we're going to say minus 2. And multiply that by, so you're going to say -4 multiplied by 4. So this point, it's going to be -4 multiplied by 4 and -0, right? Then I'm going to say plus, which is the last term, -3. Then I'm going to have -4 multiplied by 6. Right, and minus that, so -5 -3. Now quickly punching this into a calculator, so that is basically 5 multiplied by -20 and plus 2 multiplied by -16, and finally -3 multiplied by -24 plus 15, right? So 5 multiplied by -20, 2 multiplied by -16, right? 2 multiplied by -16, then we have -3 multiplied by -24 minus 15, and your answer should be -15, the determinant of the A matrix, right? So let's move on to find determinant 1. So determinant 1, just basically move this column to the first column of the A matrix. So our new matrix is going to be 60, 0, 0, -2, -5, 6, -3, 0, 4. And the determinant of that, first term is going to be 60 multiplied by -5 multiplied by 4 minus 0. We're going to have negative, that point, so we're going to have negative. So you're going to have 0 minus 0. Finally, you're going to have that. then we're going to have 0 minus 0. So the only term here which is available, because this is basically going to be 0 multiplied by that, 0 multiplied by that, this is the only term we have. So determinant 1 is going to be equals to, let's put that into your calculator quickly. So 60 multiplied by minus 5 times 4, which is basically negative 1,200, right? And let's move on to find determinant 2. So determinant 2 is formed by shifting this column into the second column of the A matrix. And this is the new matrix which we're going to have. It's going to be negative 5, negative 4, negative 3. I'm going to have 60, 0, 0, and finally negative 3, 0, 4, right? Then I'm going to do the same thing, cover up the first part and multiply that by that. I'm going to have negative 0 by 0. And I'm going to have negative 60 multiplied by 0 minus 0. Finally, you're going to have negative 3. Negative 3, and it's also going to be 0 minus 0. So let's see. Something seems to be wrong at this part of the question. Let's see. Let's do that again. Covering that and that, you'd have 0 minus multiplied by that, 0 minus 0, that's fine. And at this point, you're going to have, okay, you have negative 4 multiplied by 4. So at this point, we have negative 4 multiplied by 4, but that is 0, right? That's fine. And finally, we close that part there, and we're going to have 0, yeah. So this is, all of this is fine. So all of that will fall away. And the only term which you have to punch in the calculator is negative 60 multiplied by negative 16. Right? And so the final answer which we get at that point is negative 960. Right? So determinant 2 is equals to negative 960. Finally, we're going to find determinant 3. So determinant 3 is formed by moving this matrix to the third column of the A matrix. So let's do that quickly. This determinant is going to be 5, negative 4, negative 3, negative 2, negative 5, 6, and finally 60, 0, 0. Right? So finding the determinant of that, you're going to have 5, then I'm going to multiply it like that. So it's going to be 0 minus 0. Then you have negative 2. Then you're going to have, crossing that over, you're going to have 0 minus 0 as well. And finally, you're going to have plus 60. Plus 60, we're going to have negative 4 multiplied by 6 minus negative 3 multiplied by negative 5. And so determinant 3 is going to be 0, 0, and 60. So putting that into your calculator, you're going to have 60 multiplied by negative 24, negative 15. And the answer to that is negative 2340, right? So we have, let's write down the determinant values now. Where can I write it? Let's write them here. So let's say the determinant which we found there was negative 15 of matrix A, negative 15. Determinant 1 we found to be negative 1,200. And determinant 2 we found to be, let's see, we found negative 960. And finally, determinant 3 we found to be negative 234. If you used any other method apart from this, I guess you'd have an even longer working. Or yeah, that's what I believe. So Kramer's rule just basically simplifies how you do a problem like this with a lot of variables. So these are the determinant values. So we're going to use these to find each of the values or the final values of the nodes, which is what we're basically interested in, right? So let me erase everything, and so we can finally get the answers which you're looking for. Now this is a long video. Okay, so V1, V2, and V3 are the nodes of interest. each of them is equals to the corresponding subscript divided by the determinant of the A matrix. Right? So 1200 divided by negative 50, negative 960 divided by negative 50, right? And finally, negative 2340 divided by negative 15. Punching those into your calculator, for the first one, you should get negative 1200 divided by 15. You should get negative 80, so V1 is negative 80 volts. And for the second one, negative 960 divided by 15, you should get negative 64 volts, right? Volt. And finally, you have negative 2340 divided by negative 15, and your answer should be 156. No, all of these should be positive because there's a negative and negative, so all of these should be positive. And yeah, that's basically it. And these are your answers to the problem. Just to quickly go through this again, I seem to have made a mistake here. It should actually be 960 instead of negative 960. So your value here is actually going to be negative. Your answer should be that. Everything else is correct, and this is how you'd solve this problem.